Good morning, everyone. All right. Finally something to watch when I'm bored. Well, hopefully this isn't boring. Hopefully that's not why you're watching. Let's see how many people we got in here. We can start going. All right, hey VMA. So let's just go over real quick what we had, and then what we have now. So when we last left off, we had gotten the player capable of running. We got his heading correctly. We've got the sprite being rendered correctly. The animation states are good. So we have 2 animation states right now, and they're being changed based on user input. Okay. When I last left off, I was deciding what I wanted to do next, and one of the things I was talking about was we need a way to be able to see what the actual bounding area for the player is during runtime. And during edit time, right? So as we're actually constructing stuff, it's going to be useful for us in the future, especially when we start doing collision detection, to know where the actual bounding region for this character is, how it's accurately drawn on here, you know, what it's visually represented as. That way we can use visual representation as well as the data that we're looking at in order to debug things. That's going to be very useful. Right now we don't have a way to do that. In Gunslinger, I don't have the API. Well, that's interesting. I don't have the API for doing debug drawing done quite yet. So there is a, yeah. So there's an immediate mode API that you can use for Gunslinger in the graphics API, where you can draw certain things to the frame buffer. I don't have that set up quite yet. But what we do have is IMGUI, and IMGUI has pretty good utilities for doing stuff like that. So I figured what we could do is set that up, and I'll show you guys how to do that. I already have some IMGUI definitions set up down here. So this is at the end of the frame, where we begin a new IMGUI frame, then we do all of our UI rendering, and then we finally submit that to OpenGL to be rendered. Now the only issue with this here is that what this is going to do is do all of our previous renderings, submit that to the GPU, but then it's going to clear on the back buffer and then do all the IMGUI rendering. So if we look and see what we have after we compile and run, we should have what we had before, which is just the sprite sheet that we're doing. We should go down to the UI. It's interesting that this is staying on top. It's an interesting bug. To the IMGUI UI, we have all of this down here, right? So we're hey Arn, hey Unity. So we're just loading in images and then we're just viewing that inside of an IMGUI window. The reason we're not seeing our previous our game itself is because we're clearing out the back buffer and we're doing this instead, drawing it on top. So what we need to do actually is we need to render our game. If you tried Flex, I think, isn't that an ECS library? If so, no, I haven't tried it out. And I probably won't, not for this. So what we need to do is actually take all of this code here, all of our rendering. We need to actually put that into a render or a frame buffer, like an off-screen render target. So I do have utilities to do that in Gunslinger, so I'm going to set that up, and we're going to actually get this going. So what we need we should need a frame buffer object. And for the frame buffer, we need a render target, but that's just going to be standard texture. Okay. Let me reorder some of this real quick. I've got, I'm not using this texture anymore. Got this global player. I'll make this global as well. And we'll just clean this up. And the same for this. Okay. Another thing that I did off screen, very simple, but all of our asset manager stuff, I just ripped that out and put it into its own file. Right now everything's inlined inside of this header file, but in the future we can make a source file, doesn't matter. But for now this works just fine. And then we just include that at the top up here, good to go. Hold on, I'm getting a text. All right, let's keep going. So we're defining our frame buffer. That's what we'll bind in order to render off into this texture. So let's go down to the app update and where we actually do all of our rendering. And we're gonna wrap this inside of, actually we need to initialize our frame buffer. So let's do that real quick. So up here, we need to construct the frame buffer. We'll use the graphics API. We're going to pass in our render texture. We need to define all the parameters for the render texture real quick. So we'll do a parameter description object. Let's call this tDescription. So we have default parameters that we'll use, and then we're going to fill out certain things. So our texture format is going to be, we want RGBA, so 32-bit data, but it's going to be 8 bits per pixel. Standard definition, our magnification filter. We don't want any bilinear filtering, so we're going to do a nearest filter. Our min filtering, same thing. Although this isn't necessary because we're not going to generate maps on it, which I'll do that here. So generate MIPS false. So then we need a width and we need a height. So the way we're going to define these is actually the internal frame buffer size for our platform. So we need to grab that real quick. So get the width of that, and then the height of that. It's an RGBA, so we want 4 components per pixel, and our data is going to be null. You don't necessarily have to, these are defined within the default parameters, so you don't necessarily have to do this, but it is useful. So now we're going to construct our render target. So the render target is going to be construct texture, and then we pass in our descriptor for that texture. And then now that that's constructed, we can construct a render buffer or a frame buffer using that render target. Okay. And that should be all we need. Let's make sure that compiles real quick. Make sure I didn't forget anything. That should be good. Yep. Okay. So no crashes. That's all getting constructed correctly. And then down in our update, we actually want to use this frame buffer. So for all of this, we're actually going to wrap this inside of a, let me check the API for this real quick. Yeah, so if we go to the graphics API, what am I doing? Thank you. There is a bind frame buffer. So we have binding the frame buffer. We set a frame buffer attachment. This is we're actually gonna set the texture. You can actually, for a given frame buffer, you could set all kinds of attachments to it at different indices. So if you had like a frame buffer that's set up for multiple render targets, you could do that, and you write a shader. So that's good for things like G buffers if you're doing deferred rendering. And then we can unbind the frame buffer. So let's go ahead and just grab this. We're going to pass in the command buffer because this is a command. And then we're going to pass in the frame buffer itself, which is our frame buffer. And this is a function call, but I do like to wrap everything inside of scope parameters, like a scoping block. It's cleaner for me to read. So this is all of our code that we actually want to do into the target. And then we're going to unbind the frame buffer here. That should be all we need for that. Yeah, we just pass in the command buffer. So that unbinds the frame buffer. So this all gets rendered into this frame buffer's target, which again, we have this set frame buffer attachment. So set the render target for the frame buffer. Again, we pass in our command buffer. The texture that we want to use is this render target that we defined, and then 0. Insane to think that the original game is pure assembly. Yeah. But you use the tools you have, right? It's not insane for them to think. And this is, there we go. That should be all we need for that. So again, compile this, run it, should be no crashes, good to go. I've seen inline written in your code base. Is that an inbuilt flag or something you have custom made? There are inlines that are defined for the C standard library. Actually, it's platform dependent. So I've made my own. Let me see where I've defined it. It might be in util. No, types. Yeah. So, so something like this. So Windows has like a __ force inline. Linux doesn't have that. Apple doesn't have that. They have attributes for Apple. I think Linux has something as well, though it was acting kind of strange for me. Yeah, but there is a single underscore inline by default. But I do the thing that Casey Muratori does, which is knowing the difference between these types of statics, right? So static can mean different things in different contexts. So I like to be explicit with it and say that if it's a global static, then I'm going to use the global tag. If it's locally static, then I'll use the local persist. And then if it's inline, it's a static inline function. So just to be more explicit, that's all I'm using that for. Pislify. I always have trouble saying your name. All right, so now we're rendering everything into a frame buffer. If we don't do the UI and we don't render, actually we need to shut this all off. We should get a black screen now because it's all being rendered into that off-screen buffer. So we just have a black screen, which is what we expect. So what we're gonna do now, I'm gonna clear all this. Thank you for explaining that. Yeah, of course. So we have our, I need to rip all this out soon enough, which we'll do. Right now this is default initialization that comes with like the IMGUI examples. Same thing with this frame. Here's our render. And let's see, let's get rid of some of this other stuff. We don't need this. Don't need this. We have our image viewer. We'll call that like game scene, whatever. Get rid of all that. And what we're gonna do is convert our render target's ID. We're gonna target width and the height. And then we're just gonna render our game. So now what we should have is we should have the game. Those compiles, yeah. It should be the game, but it's in an IMGUI window, yeah. So now we have our game using the IMGUI framework rendering into this here. Pretty straightforward. Thanks for open sourcing Gunslinger. Yeah, man. I needed to open source it because I was using it for work stuff. So it's kind of like a legality thing. Also, well, not really necessarily that. It's just I didn't want any issues with it, right? And because I wanted to build a community around it. So kind of like Raylib. So if enough people get interested in it and it gets used by other people, then we could have like a small community or that grows into a larger community of people that are using it for personal projects, which would be cool. And then we could do like game jams and competitions and whatever else. It'd be fun. And it's, like I said, I made it not specifically for games. I made it for tools, right? I'm a tools developer. So it's useful for stuff like that, which is the main purpose. But of course you can do games with it. I like Raylib and Gunslinger. Cool. Awesome. Yeah, there aren't enough cool C libraries and stuff like that. Okay, so we've got our game scene here. The only thing I don't like is I don't want the ability to be able to move this stuff around. So we'll fix that here in a little bit. But now that we have this, I want a way to be able to use IMGUI's draw features because they have a good immediate mode draw abilities to be able to draw a bounding box around our player. And I think we can do that pretty simply. So what IMGUI has is that you can grab a draw list, right? So you can grab the Windows draw list. And for this, you can add, instead of using stuff like this, which uses the way the immediate mode GUI works is that it uses an actual internal cursor. And what it does is as you're drawing stuff, it's moving that cursor down over, things like that so that it can format things directly or indirectly for you. If you use the draw list, what you can do is you can pass it, like they have in, let me look at that. There should be like an add rect. But there's a specific, yeah, it's this one. Okay. So these are all the draw list functions that you can use, I believe. So there's add line, add rect, there's image, add image quad, add quad. So all these different things that you can do that it uses internally actually. So all these paths, stuff like that. But you have access to those things, which is great. So we could define something like, what's the next one? I think it's the color. And then the width. So we could put something at 0, 0 to 100, 100. And we'll give it a white color. And then we have this guy up here. Now it's in window space, right? Or in screen space. So if we move the window off, then it's outside of our clipping rect that's for this window, so we won't see it. Okay, so that's something to keep in mind. Now what we want is the ability to be able to have a border around our player that defines its bounding area that actually moves with the player, right? Also, another thing to keep in mind is that we can zoom our camera in and out. So we need to make sure that we're able to have this rect be bound to the player and represent his bounding area regardless of the camera's transformation, or respect to the camera's transformation rather. Okay, so we have to keep that in mind. But again, what I want to do is I actually don't want this to be in a window. So what we're going to grab is that IMGUI has a draw list that you can actually grab. Try to see what the... Yeah, it's a foreground frame buffer is what it's called. So instead of the window draw list like this, we can grab a foreground draw list. And instead of doing all of this, what we'll do instead is we'll draw an image to the foreground frame buffer. And we're going to do it at 0, 0 all the way to the width and the height of our render target. And then we pass in our UVs for that image. IMGUI flips things, so we're going to flip our UVs. And now we should have, it's going to look exactly like we did before we started all the IMGUI stuff. I think I misspelled something. Yeah. But now it's just our basic scene, right? So what we're doing is we're actually drawing the full width of the scene here to our frame buffer, or from our frame buffer into an IMGUI draw call, right? So we can't even tell a difference. The only way we can tell a difference is that if we change the size of our window, we're not resizing the frame buffer right now. So this was the original size of our render target. Yeah, but we get, you know, different sizes here. Okay, let's keep going. If you all have any questions about anything, just stop and ask me. Otherwise, I'm going to plow through. Let's look back. So now we have back to where we were before, but we're using IMGUI to render our scene. And now we want to draw the bounding area for the player, right? There's a couple ways we could do this, but we're going to have to do some transformations. I know off the top of my head we're going to have to, in order to be able to respect things like the camera zooming in and out, the camera moving around, if the player were moving, things like that, because we want that bounding box to be with respect to the window space. So what we're going to have to do, if I can open up Photoshop, what we're going to need to do is do some transformations in order to get this working. Wait for my drawing pad to turn on. Come on, there we go. So right now, if we look at the way that like a quad batch is defined, Bislify, if you're trying to compile right now, it should be working for Windows. But if you want to file an issue, then I'll happily look at it. So right now for our quad batch, we have quads which are defined with this information. We go negative 0.5, negative 0.5 to 0.5, 0.5. So this is our min and max of our quad, and this is in object space. Okay. And then for our transformation, what we do is we take this and then we multiply it by our camera. So we have a camera here. So we do our camera space, and we're going to move it into, you know, what the camera sees. So its frustum using its matrix. And then we take that. So this is our view space. Then we take that and we put it into perspective, or a projection, right? So we do a projection space to bring it into clip space. So this is view. And then we have our projection, which is our clip space. We normalize that, doing a projection divide. So this gives us something that goes from -1 to 1. So -1 to 1, 1. And then this we want to bring into screen coordinates so that we can actually render it to our screen. So then we need to normalize that by multiplying everything by 0.5 and then adding 0.5. So that brings us into a range of 0 to 1 inclusive. Okay. Then we can take these and we could multiply by our window coordinates to bring it into screen space. All right. So this is the transformation that we're going to have to do in order to get something like a bounding box around our player that respects when the camera is zooming in and out, when it's moving around. It also respects our projection that we have. Right now we have an orthographic projection. And then we can bring it into our window space. So when you're doing things like this, you need to understand at all times what space you're in order to do these kinds of transformations. Okay. So right now we're going to go ahead and get this all set up. Okay. So what we're going to do, let's look at the player real quick. So if we look at the quad batch, where we actually grab this information, this is all going to be useful to us, so we're going to use that. But let's define a function up here so that we can actually grab our bounds. And we'll just do it. Let's just do it right here. So we want a vec4. It's going to be like an AABB. We want the player. We also need the camera so we can get information from that camera. Let's get our platform information. We'll need the window size because we'll need to pass that into our camera in order to get certain projection information. Okay. Do you recommend a way to remember what space you're in? A way to remember. That's actually a good question. A recommended way to remember. Well, for like a typical graphics transformation, those are the ones. There are infinite number of spaces, right? If you just want to think about it technically, there's an infinite number of spaces. There's different things that you can talk about. Like if you're on a number line and you're adding floating point numbers, right? Then you're in a one-dimensional space on a number line for R1, right? If you're talking about like 2D matrices, then you're in an R2 space, right? But I wouldn't necessarily say, what's the best way to think about this? There are certain ones that you, actually this wasn't even correct. So we're not going to go directly from object to view. We're going to go from object to a model space or a world space. Okay, then we go to our view space. From here. Okay, so your typical transformations, let me go ahead and make a new layer, that you have for a graphics transformation are object space, world space, camera or view space, projection, or clip space, right? Depending on which part you're in. And then you'll have NDC, which is they're kind of the same as this, but you can separate them depending on which steps you want to take. And then you go to screen space or, window space, whatever you want to call it. Okay, this is your full graphics transformation that your GPU is doing. The ones that you're in control of, your GPU will do these last two for you. But you have full control over how you want to set this up. These are the ones that you typically handle yourself, at least in terms of how you're transforming vertices, right? So if you want to think about when you pass in vertex information to the GPU, you're passing in object information, okay? So when we pass in like our quad batch, we're passing in something that looks like this. It has vertices that are defined like this. 0.5, negative 0.5, negative 0.5, 0.5, 0.5, 0.5, okay? And if you want to be explicit, we can add pluses to these. Right, and actually it's something like this, depending on your winding order. It's not a quad, it's two triangles, right? So we pass in a set of triangles represented as a quad to our GPU, okay? This is what the GPU sees. So what it's going to do for each of these vertices is it's going to go through and it's going to perform this transformation. So we're going to combine all of this stuff into a single transform, okay, which is typically defined as our MVP or model view projection matrix. It's going to use that information, transform each of these points, each of these vertices into our NDC space, and then using, which again goes from 0 to 1. So it's normalized device coordinates. That's what NDC stands for. And then we're going to take that NDC information and using our window space, our window coordinates, right? So if we have something like a screen display that's 1920 by 1080, we're going to take our NDC for our vertex that's transformed, and we're going to put it someplace according to our window space, right? So if we have something that's in NDC like 0.5, 0.2, that's 1920 by 1920 times 0.5 and 1080 times 0.2. And then that's our final coordinate in window space transformed all the way down this pipeline for this original vertex. So the best way to remember your transformation space, whatever transformation space you're in, is to think about what point in this pipeline, at least for a graphics perspective, what point in this pipeline are you actually, what are you in, right? Are you in object space where you're talking about actual vertex information? Are you in world space? Like when we're dealing with bounding box collisions and we actually want to interact with the world, we're going to be in world space, right? Are you in view space where we're actually interested in what the camera sees and how those things are manipulated within the camera's perspective? Are we in our projection space where we talk about actually projecting that into a frustum, right? A normalized frustum. Are we in NDC where we actually take that normalized frustum that's -1 to 1 instead of cubic space, and we move that into NDC where it's a 0 to 1 space instead? with no Z coordinate? Or are we in window space, right? You just have to keep those things in mind. What helps for me is that I've written software renderers before where you don't rely on the GPU to do this stuff for you. You actually have to do it all. And actually right now we're going to write like a mini software renderer in order to handle this. So you guys are going to kind of see the full transformation of a vertex all the way down. So buckle up, get ready. Hopefully that answered your question. So yeah, so with this window bounds, so we're interested in this, right? We want the full transformation. So, like I said, we actually have all this information down here in our quad batch that we could use directly. So I'm going to copy this. And paste it here. And delete out all the stuff that I don't care about. I don't care about setting the current frame. I just care about the current frame. We want to get the frame from our animation. We care about the width and the height. We care about the UVs. Actually, I don't even necessarily think we care about the width and height. We want the size of the sprite. Yeah, so the width and the height. Yeah, you're welcome. You are welcome, Dirty Mint. Quad info we don't care about. What we're going to do is define an actual model transform. So let's walk through this real quick, okay? And actually I have some notes here on the side. What we're going to do is actually define a VQS transform. So this is a construct that I have in my framework, which uses VQS transformations. VQS stands for vector, quaternion, and scalar. It's kind of a misnomer because I don't use a scalar for this last part. It's actually another vector, so it really should be that. But this is a standard construct that's used in game engines or graphics applications. It's a way to be able to handle matrix manipulations without having to deal with a lot of complex matrix transformations. You could pass in, this is what Unity uses, this is what Godot uses, this is what Unreal uses. Pretty much any standard game engine will use something like a VQS. So what you could do is inside of this transform, you're able to set your position, you're able to set your rotation, and you're able to set your scale. Those are really the three homogeneous transformations that you're interested in with 3D objects that you want to do for a graphics application, right? You want to be able to translate something, you want to be able to rotate it, and you want to be able to scale it, okay? So this transform allows you to be able to set all these things, and then with a final call to VQS to mat4, we can pass in our transform, and it will give us our final model matrix, okay? That's what we're interested in. Instead of having to multiply a bunch of let's see, mat4 mul I think is like a bunch of different matrices together. So you would start out with like an identity matrix and multiply that by see, it's TRS. So you would translate it first, or you scale first. Sometimes I forget this. I think it's scale, rotate, translate. Right, so we do something like this. We don't have to worry about doing that. This handles all that for us. Which we will set that down here. We don't care about this. We don't care about any of this information. We care about, let's call this X form. So the position. That's all we need for that. Okay. I'm using G player everywhere. Let's actually set that to the player that we're passing in. Scale factor. So we're setting for this transformation, we're going to set our position, which right now we're just going to use 0. We later on need to add like player information, like where he is in the world. Actually, in the world, or later on, we'll have, for the player as an entity, we'll have the player having its own transformation. So we won't even do this, right? We'll just grab the player transform directly and use that in order to grab our model matrix. Okay, but here we have our model matrix. One thing we need to do so that we don't mess up our multiplication here in a second for our matrices is we need to set this scale. We need a constant value of 1 for our z. We don't want that to grow any larger because it's going to mess with our matrix multiplication later on. So what are we returning? We actually are interested in a vec4 for our bounds. This is going to be like an AABB of the player. Okay. I'll put this down here. All right, so we want to define the object space quad for our player. Okay, so that is this thing. We're interested in defining this. Which, again, if we look at this top left vertex, we'll call it top left. And it's going to be negative 0.5, negative 0.5. Okay, so that's that version, or that vertex, and then the bottom right one is positive 0.5, which again I'll be explicit to positive 0.5. However, we need these as vec4s, and the reason you need that is because if you're doing matrix multiplication, so you have some MVP matrix, which we're going to have, which is a 4x4, we need to be able to multiply that by each vertex, right? And we can't do that if it's just this. This matrix math doesn't work. This is a 2x1. What we need to do instead is make this a homogeneous matrix so that we can do that transformation. And we're going to need to add some information here. So we need a z and we need a w in order to make this possible to be multiplied. So we'll have a 4x1. If you're ever wondering whether or not you can multiply two matrices, this is how you determine the dimensions of a matrix. You go up and then over in order to write it out. So this is a 4 by 4 for our MVP, and then we're going to multiply that by a 4 by 1, and then you look at these two inner dimensions right here. If they equal each other, then you can multiply the matrices together. If they don't equal each other, then you can't. So just keep that in mind. So again, with the other one, we had 4 by 4, and we were trying to multiply it by just x and y, and that's a 2 by 1, and we can't do that operation. It doesn't work. So we have to add our z and w component in order to make that work. So let me show an instance of a shader that does something like that. If we actually look at the quad batch shader down here, so this is our full transformation for a single vertex that I was talking about earlier. So we have our projection matrix, we have our view matrix, which we get both of those from the camera. We have our model matrix, which is our models transform, which puts us in the world space. And then we have the actual vertex information, which is an object space. So this A position is a vec3, so it has X, Y, and Z components. And then in order to make it a homogeneous 4 component vector, we're going to add in a 1 for our W. And it needs to be a 1, it can't be a 0. It's just the way that the math works out. Okay, so let's go ahead and do that. So down here we have a 0 because we don't care about the Z component. We're in 2D space, right? So we don't care how far we are in the world in depth. It's an orthographic view, so it's always going to be squashed to the screen. And we want 1 for our W component, and that completes our vertex information. Okay. So we have that. Now what we want to do, again, we have our model matrix that's a transformation matrix. Let's go ahead and say define matrices for transformations. Now we want our view matrix, because again, if we look at this, we wanted to figure out what this is. And we have the ability to do this in Gunslinger. You just get the view and it gives you a view matrix, and so we can just pass in a pointer to the camera, which we have there. And then we want our projection matrix. We have the exact same thing, just with projection, and we can pass in the camera, but we also need to know the dimensions that we're gonna, like the bounding area, right? So we need to know the size of the window and the size, so the width and the height of the window that we're actually using for our projection calculation. And then we can define our final matrix, which is this chain right here. We're going to multiply those together in order to give us a single MVP matrix. Okay, that's our final MVP matrix. Okay, so now we have, if we look at our space, after doing all of this, we're now complete with this transformation. Okay, so now we're in projected space, okay, or clip space. Now we need to transform ourselves into NDC, okay? And the way we do that is we have to do something what's called, actually we haven't even done that yet. We've just defined our MVP matrix. We actually need to transform all of our vertices. So the way we do that is there's a function in Gunslinger where you can take a mat4 and multiply that by a vec4. And so we're just going to pass these in. All right. So now that transforms us into projection space. And now you have to do what's called a perspective divide. Because whenever you multiply this, you've added this W component, right? This data wasn't there before. It now gets added into this new transformed vector. So we can call this something like X prime, Y prime, Z prime, and W prime. This W prime is biasing all this data. So what we have to do is take this W and divide it through I disconnected for a second, so let me look at where that stopped. What I was saying before I get disconnected was that you have this matrix information. It's going to be biased by this W component of your transformed vertex. And what you have to do, and again, we're not interested in this necessarily, what you have to do is you have to unbias that. So we're going to do a perspective divide where we're going to go through each of these components, divide by that W, and that gives us a final vertex transformation that is going to be in correct projection space, which is everything divided by the W component. So that gives us a W component of 1. So that's what we're finally looking for. Very simple to do. I know that looks like it's a lot of information, but all we're going to do now is after we've multiplied by our MVP matrix for each of these original object space vertices, is we're just going to do a simple vertex divide. And all we have to do for that is we have to scale the matrices. So vec4, we have a scalar operation, take that, and we're just going to divide by 1 over the W component. Okay, or multiply by 1 over the W component, because that's what scalar does. It's just a multiplication operation. And that gives us our accurate perspective divide. I'm going to compile real quick, so we've gone for a second without any compilation, just to make sure I haven't messed anything up. Yeah, okay, so up here, sprite frame animation T, it's got to be, yeah, there we go. Transforms undeclared. Yeah, this is X form. And we need to return our bounds. Convert from vec4 to, did I not? Oh. should be good. Okay, it should compile the same. All right, so we've done a perspective divide. Out of curiosity, where'd you learn your linear? Well, I took linear in college, so that helped a lot. I had a good professor. But for all this stuff, I actually took a graphics course in college where we wrote a software renderer, and that really helped. So learning, if you get the chance to write your own software renderer, you'll learn the math, and you'll get a better feeling for actually what's happening to all your vertex information when you pass it down to the GPU. Because right now it's a black box for most people. You have certain functions, you call it, and you just hope it works, right? But if you actually understand what's happening at the transformation level, then you can debug things a lot easier. You can write your own software renderers, So I recommend doing that if you get a chance. There's actually stuff in here that we're not even going to cover, like learning how to actually do clipping certain information, doing Bresenheim algorithms to clip lines and all that kind of stuff. But we're not going to cover that because we don't need to. All the clipping information works in IMGUI, so it's kind of black boxed away from us. So yeah, just doing it. So we have a perspective divide, and now the final thing we need to bring into NDC, and then we need to bring into window space. Okay. So let's actually see. Yeah, and if you get a chance, take a linear. I don't know what it is like at other universities, but for ours, we had a choice to do linear with the math department or do it with the computer science department. The computer science department was much more engaging and rewarding. I'll say that because you actually had real world examples that you could use the math and actually find its applications, and it made it that much more interesting, and it made the information stick, right? But again, I was already working at a game company on the engine team whenever I was doing linear in college, so it helped to reinforce the stuff that I was using on a day-to-day basis, but not really fundamentally understanding. And then again, that graphics course really helped. Even though we wrote a software renderer in Python, that was something. So again, we want to transform this to NDC and window space. So for and again, let's look at what that math is. To do something like that, it's very straightforward. We're just going to normalize. So we're mapping a range. Right now we're at negative 0.5. Or no, we're at -1 to 1, and we want to map from 0 to 1, right? So that we can get to window, because there's no negative window coordinates. So what we're going to do is we're actually going to map that range. It's very simple to do. So we're just going to multiply it by 0.5 and add 0.5. So if you look at your range of something that's like -1, this is your bounding range right there to 1. If you multiply both of these by -0.5, then you get a range of -0.5 to 0.5. And then if you add 0.5 to these ranges, you get 0 to 1, which is what we're doing. Okay. We'll do that for all of yeah, if you're trying to do it without understanding linear, it can be tough. You can do it. I doubt that most people who do games really fundamentally understand linear, but they know how to use it, right? It's like I've said this before. Like I do woodworking, but I'm not an electrical engineer and I'm not a mechanical engineer, but I know how to use a table saw. You know what I mean? It's kind of the same thing. So this one is actually tricky because our y is going to be flipped, right? So we're actually going to map the range in a different way. Actually, we'll do that in a second. We're not doing that now. So we're still going to do the same thing. So we're going to do and then br.x. Okay, so now we're in NDC for all of these. So these are now all in a 0 to 1 space inclusive. And now our final transformation is we want it in window space. Okay, so we want to be able to take all of this vertex information or the bounds information, and we want to transform it into window space. So for most of these, it's going to be pretty simple. So we're just going to multiply by the window coordinates, which we have up above. So right, because now we're in a 0 to 1 normalized range, and we want some that's going to act as some percentage of our window coordinates. We're going to do the y's here in a second. I'll tell you why, because it's going to be a little different. Okay, so x components are easy. The y components are different because they have to be flipped. So we could take that and then subtract from 1 the y component, right? So tl.y, 1 minus that, multiply. There's also a mapping range that I'm going to use that I have in Gunslinger. So we're going to take the original coordinates, but we're going to flip them, and we're going to now map that to the range that we're interested in. And that's going to be tl.y times ws.y. And then we're going to do the exact same thing down here. And again, that's just because the texture is going to be flipped. That has to be flipped from the window coordinates. So now we're going to set our final bounds, and it's tl.x, tl.y, so that gives us the top left corner that we're interested in, and br.x, br.y, that gives us the bottom right corner. That is our full transform vertex information. This should compile. Okay, right now we're not using it, but let's go down to the do UI function. So right now we have this image. We want to grab the window bounds for the player. I used to build electric guitars. Cool, man. That's awesome. Yeah, very cool. My stepdad builds cigar box guitars. I'd like to build a couple. I play guitar. Actually was a music major before I switched over, and guitar was my main instrument. So get the window bounds. Cool. So player bounds, just call PB, and we're going to get the window bounds, and again we're going to pass in our player and our camera. Thanks, Jeremy. See you later. Thanks for dropping by. Like and subscribe. I'm going to shill myself real quick. Everyone else, if you're not subscribed, do it. So we got the player bounds. So now let's draw bounding rect around player. And this should work. First time. Always does. So the way this function works, again, you're just drawing a rect to the command buffer information, all the vertex information for IMGUI, and it's going to be the foreground draw list. So this is like an overlay. So anything that is underneath this will get drawn on top of it, which actually might not be what we want. We actually might want to make this the background draw list if they have something like that, and then we could still do IMGUI windows on top. That'll probably be useful. So we could have like a tile editor that's up and we could drag tiles out and construct shit. So, but the way this works is you pass in one vertex, you pass in another vertex, and then it draws a rect between them. So this is your min. This is your max. And this is the color that you want to use to color the actual rectangle. And this is the line width. Okay. All right, so for this, we have our top corner, we have our bottom corner, not BR, pb.z, pb.w. That's how we've defined that back 4. Again, it's basically an AABB. And let's see what that gives us. Oh, well, I see something up there. So it looks like we are scaling it, but it's like it's transforming a little oddly. Huh. I wonder. It might be the way that IMGUI draws these rects. Let me do. If we do a line from pb.x to pb.y, let's see, pb.z to pb.y. So we're just going to move in the width. So it should be the bottom left corner to the, or the top left corner to the top right corner. That's what I'm thinking. Comment this out real quick. Where are you at? Why don't I see you? Okay. Let me see. What did we mess up? So again, we grab the animation, we have the count, grab the UVs from the sprite itself, which is our dimensions. That gives us pixel coordinates to give us a scalar for our world space scaling. We define our transform in order to give us a world space or a model space transform to put us in the world. That all looks correct. Define our bounds. These are our vertices, top left, -0.5, -0.5 to, let's just make sure this isn't screwing it up. I doubt it is, but trying to be clever, maybe that's messing it up. Model matrix, good. Camera to our view, projection matrix, we're passing in, again, the window size, get our window dimensions, which that is correct. And then defining our vertices, that is good. Scaling, so we do a perspective divide. Okay. We do an NDC for every single one of these. Make sure I didn't mess any of these up. That looks good. TL, BR, BR, X and Y, yep. Y times Y. Okay. This all looks right. range 6 y. Yeah, that looks right. So there's got to be something the way that I'm rendering it down here. That's got to be it. Is it the wrong? What am I missing here? So like, why for the? Okay, so what is that doing? It's like way up here, offset in a really strange way. I'm not 100% sure why. It's got an odd offset. You can see it grows correctly though, so the width is fine. That looks correct, but the Y offset is incorrect. And again, I'm wondering if it's maybe the way I'm mapping this stuff. So maybe instead of this, I can pull this all into a single function. Maybe I'm mapping it incorrectly. Let's just do it all together. I'm thinking maybe I'm messing something like that up. Oh yeah, hold on. That's the problem. So I'm being dumb. I don't want to map this entire thing. I just want to map this range to give me 0. Oh, that was stupid. Okay. So here's the stupidity I did, stream. So this takes anything you give it into a range. You give it a starting range, and you give it a final range, and then it takes whatever value you have, and it'll map it into that. Does anyone see a problem with the way I was doing this? So I'm taking my NDC, which I want to be 0 to 1, which it is, right? This 0 to 1, and then I'm multiplying by my window space, which I want to get outside of 0 to 1 out of normalized range. I want it to be in window space, so it could be anywhere from like 0 to 19, or let's say for this 1920 to 10 by 80, anywhere from 0 to 1080, but it's clamping that down to a 0 to 1 space. So I need to take that out and multiply by that, like that instead, so that I'm actually respecting window space. Well, that's the issue. There we go. So now we have our bounding area, which respects our camera. We move the camera around. It respects the view space. It respects our projection. So whenever we zoom in and out, it'll respect that scale. And then it grows with the player bounds. So it's respecting the world space bounds of the player. And it doesn't matter if we do left or right, because that quad is just the UVs that are being flipped, right? Cool. See what time it is. 10:35. All right, I got like 30 minutes. So that was kind of the main thing that I wanted to touch on today, was doing that transformation. and explaining graphics transformations. But now that I got a few minutes to kind of play around with, hey bro, how are things going with the project? Pretty good. So we're rendering everything into a separate frame buffer, and now we can do overlay debug information using IMGUI. We can also, let's say, how does this actually work? Let's see, IMGUI, add image. Yeah, so then we can just pass in like now we can tint our entire game if we wanted to. So we could have like debug information where it's like this is this particular layer, and then we could, you know, I don't even know why you do this. I'm sure we could have some reason to be able to tint the entire game screen a certain thing if we wanted to. But really the use of this again is going to be in collisions later on, so that we can know where the player is, we can know if something is interacting with it correctly according to its bounds. And again, what we're doing is we're representing world space bounds, but we're displaying that in window space. And again, this is all in, I think if I just do like an IMGUI window, let me wrap this. Yeah, so this is all foreground element stuff, so we're not going to even see this. Now I wonder, does it have IMGUI have a get background? It does have a background draw list. So let me see if this works. Super. Okay, so now what we can do is render our game, and then any debug window stuff that we want to have, we can just pop that up whenever we want, and say we have like tiles that we want to drag out into the world or something like that, right? Or have debug information that's, man, my mouse is acting weird. Stream's slowing it down. We have like debug information for a particular entity or something like that. We can display that up here, you know, whatever we want to do. So that will be useful. In fact, we could do like, I don't even know what we want to do. B32. Let's just say like, let's do some camera information. So projection type. We could do the FOV, near plane. That really won't matter. Let's just do the ortho scale. So F32 ortho scale. Don't even need to. Did the slider float? It's been a while since I've actually used IMGUI. So we'll do like camera ortho scale. And we'll just pass in the ortho scale of the camera. And we want to go from like, I don't know, 0.01 to 10. So we do like some debug camera information. What did I miss here? What's the problem? What did I miss? Do I need the format? I don't think I need the format. No overloaded function takes 0 arg. Oh. Well, I don't think that's... It's still complaining about something. 494. Jeez. Come on, I'm GUI. What are you doing to me? We'll take a label, address, that. Do I need... Holy Lord. 2 arguments. Oh, it's missing a comma. Jeez. Anyway, so yeah, now we could have debug information for our game. So just throw this up here. So just controlling the orthographic scale for the camera, which is like a zoom feature. Yeah, cool. That's a good setup. That'll be useful. We could also have probably, like I was saying before, have like a tile menu, and we can drag tiles out so we can edit the world. Yeah, a lot of stuff that'll be useful for. What's up, the Fiac? How's it going? So I think that's all I wanted to get done for today. A couple of things. I did make... Let me open this up. I did make a repo for all this. So if you guys are interested in following along, I'll keep checking this in after each stream, so you guys can keep up with the latest. You can download it, mess around with it yourself if you want to. You could probably work on it faster than I can, since I'm only able to do this for like an hour and a half each day. And yeah, but it has everything in here, and again, I keep it up to date. It's 2 days out because I didn't check in yesterday because I didn't stream yesterday. So, but the whole purpose of this project is we're gonna recreate the first level to Contra, and we're gonna have a lot of interesting challenges along the way, a lot of interesting game engineering and just basic engineering concepts that are going to be touched on. Like today we went over the graphics pipeline. If you missed that, you can rewatch the streams. I go over what your GPU does in the back end, some of the math that's involved in there, and then we kind of use that in order to define or to do a software rendered quad right here that's actually projected into screen space. And we use that for our bounding box information. So I think for the next one, what I'm going to do off screen is probably finish up some animation states. So we've already gone through animation states, but there's some art that I need to edit. That's boring to watch, so I'm not going to do that on stream. You guys have seen it. You don't need to watch me do it. So have some animation states that are done. So we'll have like jumping, crawling, being able to aim the gun up and down depending on the player movement, right? So if I hit up and down, the gun should move. And then I think we need to start constructing levels. So we need to start thinking about that. That's going to involve being able to have custom scene data, like tile data, be able to construct worlds, be able to serialize all that information out. So I'm going to show you how to write a serializer to be able to load and reload custom assets. So our scenes are going to be assets. Yeah, I mean, there's a lot. I also have a requirements doc here. So this goes through, and it's just basically requirements for what we kind of consider that we'll need for this. Right now I have finishing the player and animation states. We're gonna have to do player movement. Yeah, so a lot of stuff in here, and we'll continue to add on stuff and then check stuff off. And you know, when you add one thing, or when you take one off, you add 10 more, that kind of thing. So I'm not sure how long this project's gonna last, but there's quite a bit that we can add into this, and we can go in pretty far depth into a lot of this stuff. So, yeah. But I'll chill for a second, and if you guys have any questions, then I'll ask those. But if not, then we're gonna call it for today. Again, I'll put a link to this GitHub in the description real quick. Okay. Check out the description. It has a link to the Discord, has a link to the project repo for this. If you guys want to download it, check it out, follow along. If you find any issues with it, you can just report an issue. I'll look at it. It should compile for Windows, Mac, and Linux. If you have any trouble with any of those, let me know. If you get it compiling for one and it had an issue, please file a report, and then I'll pull it in. What else? Like and subscribe, you know, all that jazz. Gunslinger SandSim question. Sure, what's up? Also, I need to work on if you guys, if any of you are like OBS or YouTube streaming gurus, I need to look at getting the lag down for all of this. Where did you get your implementation of the bright and bloom shaders? I have, let me pull it up. So I got that from previous shaders that I had written for Injon. So let me pull that up. Post-processing, nope. This is all very well organized. Jeez. Yeah, there we go. So there should be a bloom in here as well. You compute the taps on the vertex shader? Yeah, I do. So look inside of here. This is Injon, which is my C++ engine. And I just took the brightness shader from here and just reworked it so that I could use it. So I had to change some vertex information so I could make it 2D. Well, no, that's not right. I had to change certain things, but... And then I have a bloom shader as well. Let me find that. Yeah, it's just a Gaussian blur shader. So just inside of here in the main tree, just look for, there's a horizontal blur and vertical blur, and there's vertex. So there's this one, there's vertical blur. Can I correct that? So just look for the blur shaders, and that's kind of, that gives you your bloom, right? For that I use different types of blur, at least in Injon, and then I composite those. For the SandSim, it's pretty straightforward. It's just one. The shaders assume a full screen quad as input, right? They'll assume whenever you pass it. I mean, you don't have to assume a full screen quad, right? So whatever your vertex information. If you look at you look at the vertex information, the declarations they're basically set up for a full screen quad, right? So it's a vec2. Let me look at this. So it's a vec2 for the vertex position and then a vec2 for the vertex UV. So you could say they assume a full screen quad, but you can do it with whatever. Have you watched Cherno? Yeah, I've watched Cherno. Who hasn't watched Cherno? Someone earlier was asking about what she refers to, or C++, C. C, very much so. Someone was asking about, in the Discord, about extending this in order to write their own custom platform layer for Gunslinger. I allow that. All of my APIs that the engine uses, like actually let me look at that real quick. So this is the engine context. And right now what's defined are platform layer, graphics layer, audio, and then you pass in an application description for your application. All of these interfaces are redefinable. So the way that they are used is it assumes that you're going to fill out one of these platform interface structures and you're going to supply your own function pointers to fill these out. Or you could just take the existing platform interface and fill out your own function pointers. So how is this used? Well, I have a glfw implementation which does exactly that, right? So it fills out all of these platform interfaces. So it overrides this platform construct. Or actually it compiles with this platform construct. So it implements the platform construct and it fills out all this information and then returns an instance of the platform that you want to use. Same thing with SDL. So there's an SDL platform. So I don't think it's up to date. I think I haven't been working on this one as much, but it does the same thing, right? So it implements this platform construct, fills out all the information, uses whatever implementations you want to use for the function pointers, and then it passes that back to the engine to use. So if you wanted to write your own platform layer, you could do that. And then when you're compiling the engine, so like down here, you would feed in whichever platform layer you want to use, like right here. So if I wanted to use SDL instead, I could redefine this to use the SDL layer and then just supply it into here. And now I've compiled with an SDL backend. Okay, so that's totally possible. Same thing with the graphics. Right now I'm using an OpenGL layer that comes shipped with Gunslinger. You could go into the graphics API. So it does the exact same thing, this graphics interface. And you could define your own graphics interface, fill out all this information, and it should be good to go. Or you actually don't have to fill all this information out, right? So a lot of this stuff might not even be used because this is defining more implicit commands that you would see in implicit language like OpenGL. But if you had an explicit language like Vulkan, some of this stuff wouldn't make sense. So you would want to do stuff like defining pipelines and stages and things like that, which actually I would in the future would rather move to that and have an explicit interface that you use for everything, and then in the back end for like OpenGL, I'll take the explicit interface and I'll convert that into an implicit interface so that the user doesn't have to do that. But then we have this OpenGL. This is the actual OpenGL implementation that's used in the backend. So that's gives you a little bit of insight into how this stuff is used. So for the guy that was asking that in the Discord, that's kind of how you would go about doing that. But if there aren't any other questions, I think I'm about to hop off. And I probably won't stream over the weekend. Try to keep this mainly to a Monday, Friday thing. Weekends, I have other stuff I have to work on, so. But it was me probably. Maybe. I don't know. Everyone's names are different. Are you Karishi VMA? Do you program C for a living? Yes and no. So my day job, we mainly do Android, so it's a lot of Java and Kotlin. But all the external tools that I write for that job, like written some texture compression stuff, conversion tools to go from like 32-bit down to different versions that we use for certain architectures. It's like 8-bit and 16-bit. All that stuff is done in C, and I use Gunslinger for it. So all of that's why I wrote Gunslinger, by the way, guys. It's I used it for work. Needed something to do these side tools that I needed to do for work, so I wrote an open source framework just in my free time, and I use that for just a bunch of different tools. And now I'm sharing it with you. Koreshi. Yeah, cool. Okay. Yep, that's how you do that then. I'm glad you're here. Oh. Alrighty, dudes. Well, I'm going to hop off. But thanks for joining. Again, like and subscribe. Helps me a lot. Keeps me motivated at the very least. And then sub if you haven't. Join the Discord if you haven't. Download the project and play around with it if you want to. If you guys come up with cool ideas, surprise your work can't lay claim to this code. No, I've done it all in my free time. I don't work on it at work, so they can't do that. There's no clause. The reason I would like my job, by the way, is that there's no moonlighting clause at where I work, so I can work on personal work and not have it interfere. It's part of the beauty of not being at a game company, which, by the way, is why I don't work in AAA and why I've turned down jobs in AAA for that reason. But that's a discussion for another time. Alrighty. Okay. I'll see you guys later. Thanks for joining. All right. Bye.